Okay, good morning. Today we will talk about a spatial graph theoretical model to describe neuronal connectivity. First of all, we will make an introduction to graph theory. In second instance, we will talk about two classic models. And in the end, we will propose a theoretical framework able to reproduce experimental findings. First of all, the connectome is the ensemble of connection in the brain. The connectome can be modelized by a directed graph. That the graph made up by nodes, which are the soma of the neurons, and by connection or edges, which are the connection between neurons. However, until now, there is not a theoretical framework able to explain brain connectivity. There are two main variables when we talk about graph or random graph in particular. The first one is the degree, which is the number of connection of a node. It can be in degree, so that incoming connection, or out degree, which represents the number of the outgoing connections. To each degree sets, we can associate a probability distribution. They are the degree distribution of a graph. We can distinguish in the in-degree distribution and out-degree distributions. First of all, we introduce the exponential model. The exponential model is a model, the orange one, which has an exponential behavior in the degree distributions. This model has few nodes disconnected and an exponential tail, so the tail decays very fast. Then we have the power law model. A power law model is a model which has a power law behavior in the degree distribution, so that the blue one. And it has a large amount of nodes purely connected and a very slow decay in the tail. So it's called the heavy tail graph. However, experimental finding and data-driven models suggest us that in brain connectivity, we have few nodes disconnected, like in the exponential model, and an heavy tail behavior, like in the power law model. In order to fix this issue, we introduce a new concept, the concept of convolutive model. A convolutive model is a theoretical model able to combine the considerable aspect of the power law model and the exponential model. All this is performed using the concept of convolution. Indeed, we use the fact that the distribution of the sum of two independent random variables is the convolution of the distribution of the two independent random variables. Using this technique, we are able to mix the power law model with the exponential model, obtaining a graph with a few nodes disconnected, as we can see in figure, and an heavy tail behavior. However, most of the experimental finding and data-driven model are spatial graphs, so that we have information on position of nodes. Okay, today we will talk about a convolutive model able to reproduce the inhibitory network calculated by Markram in 2015, which is a data-driven model, so that it is a stochastic model, but it's strongly based on data. So it does not give us an explanation on how the network was built, something like the neural networks, to understand better. We explain this experimental finding that we will assume that it is an experimental finding using a convolutive model, which is a power law spatial model on the power law component, and Erdőr-Rényi graph in the exponential model. I was forgetting. We reproduce the physiological layer distribution to achieve spatial characteristics of the model. The results can be seen in figure. We were able to reproduce all the range of the degree distributions. In particular, out-degree distribution and connection-led distribution emerged from the model. So, what's the idea? We achieved a model, a theoretical framework, able to explain with simple rules brain dynamic in connectivity, so that we have a model to explain brain connectivity in particular, at the level of the cells, so not macro connectivity or mesoscale, but at the cells level. Here it is a list of our contribution. Thanks for your attention.